In this video, we're going to demonstrate testing an incoming motor, and that's going to be done prior to cleaning the motor. This is done at Allen's Electric Motor Service Shop in Vivian, Louisiana, and I'd like to thank Allen's for giving us that opportunity. The tester today is going to be the Megger AWA4 12,000 volt test set, and that tester is capable of doing both low voltage and high voltage testing. Low voltage and high voltage testing is used to determine the integrity of the ground wall insulation dielectric as well as the turn-to-turn dielectric. Low voltage testing is testing where you're measuring the electrical parameters at or below nameplate bus voltages to determine a change in the electrical circuit's properties. You're not stressing the winding insulation when you're doing low voltage testing. High voltage testing, we're testing the insulation at levels like those that the motor experiences to determine the integrity and reliability of the entire insulation system. Both low voltage and high voltage tests help us determine and define the insulation condition with respect to its end of useful life. Before we proceed, let's talk a little bit about high voltage testing. A lot of people are concerned when you say high voltage test their motors, especially if they're installed motors. But motors that are in the field and starting and stopping, I actually see high voltage transients and spikes when they are started and stopped, as much as 4 or 5 times bus voltage. So it's not like we're doing testing that they're not seeing in normal operation. What about a stress test? How many people have had a heart stress test when they put you under a stress situation? Same thing with insulation testing. Will it react the same at 12 volts as it will at 4 times line voltage? The point of predictive testing is to find out before we have a failure. To get there, we need to bring the stress level up on a motor to the level that it sees in real life in operation and see how it reacts. If we do not stress the insulation to the levels that the motor sees during normal operation, how can we be sure the insulation system is reliable? Let's never forget about safety. Safety is a major concern when performing motor tests. A static motor test program is designed to determine the health and reliability of motor insulation systems while the motor is de-energized. High voltage will be present on the test leads and on the equipment under test. Test equipment will supply voltage and current levels that can shock and even electrocute a person. Static testing is done and performed when it's not operating, disconnected from the power source and locked out. It is important that everyone and anyone performing testing of motors understands and follows the lockout tagout requirement at their facility. They follow the equipment manufacturer safety and information guidelines. Be sure to follow proper discharging procedures and practices following any test of a motor winding. Here is the motor we'll be testing today. This motor is heavily contaminated. Both ends of the motor appear to have contamination and buildup on the coils. It even seems to have some oil maybe inside the motor. This end has stub connections which sometimes can contribute to surface leakage and tracking rather than horseshoe connections. There's just a lot of buildup on these windings. Here's a nameplate on the motor. It's a 200 horsepower. It's a 1785 RPM at 2400 volts, AC 3-phase. Here's a technician hooking up the test set. First leads to connect are the low voltage leads, so we'll do the resistive imbalance test first. These are Kelvin leads where they're more accurate than just standard lead connections. It's very important with Kelvin leads that you connect both sides of the clip very well. Both sides of this clip, lead clip, is used in calculating the resistance of the winding. It's a very accurate test. So it's certainly important that there's no grounding of your test leads or connections, and certainly there's good connections between all phases. Now this is the AWA test set. Zoom in on it a little bit here. Try to get you a good video of the screen capture here. This is a Windows-based software program Megger provides with this test set. You click on the icon AWA and the Baker software will open. He's going to select a database that's already preloaded into this test set. And he'll be looking for this motor application. There's filed there motor tests. The motor IDs or motor are actually identified by job numbers. So he's searching the job number for this particular motor. That appears to be the one. This opens the test window, which displays the tests that will be performed based on the test ID that was pre-programmed for this motor. First, the resistance imbalance test is a copper-to-copper resistance imbalance test. Next would be a megohm straight ground wall test at low voltage. And if that is successful, we'll proceed on with a polarization index. That's a 10-minute meg test. And then that'll be followed with a step voltage test, and then finally a surge test. Now the step voltage and the surge are the two high voltage tests, and they won't be performed unless all the low voltage tests are successful. And our megohm result is at least a minimum of 100 meg. We can select the buttons on the right here and and be able to see the actual parameters that all the tests are set up for. The resistive imbalance looks like it's set at delta 3%. And the corrected value for our resistance will be corrected to 25 degrees C. Copper is corrected to 25 degrees C. Insulation is typically corrected to 40 degrees C. Next, we're going to open the window for all the ground wall tests. We know we're going to have a megohm test, which is a 1 minute test, a polarization index, which is going to be a 10-minute meg test, and a step test. We said our step test is our first high voltage test. The step test, we increment voltage in equal increments and expect to see equal increments in leakage current. The megohm test is done at 2400 volts, which is bus voltage for a 2400 volt motor. It's performed for 60 seconds, and our minimum trip ratio is 1000 microamps. The PI is the same test for 10 minutes. We expect to see an increase in resistance over 10 minutes of at least a 2 ratio. The step test will be performed at a full target voltage of 5800 volts, which is 2 times plus 1000 line voltage. The way the step works is voltage will be increased from 2400 to another value, and the charging current will dissipate. And after 60 seconds, there'll be a capture of the leakage current level. Then the voltage will be increased again to another value. Again, wait 60 seconds, capture a leakage current value, and continue all the way up until we reach 5800 volts. Those end of step values should actually draw a straight line, and therefore that would indicate that the leakage current is remaining very linear as voltage increases are linear. If we click on that config button, it opens the configuration page and configuration wizard, and we can see the different voltage levels that the test set calculated so that they're equal intervals. The test set will step from 2400 volts to 3250, which is 850 volt step, and then a 4100 volts, that's another 850, 4950, that's 850 step, and then finally 5800 volts. So each of those voltage steps is very linear. Each step will be held for 60 seconds, and our minimum meg threshold for any time during these tests is 100 meg. So we can close out that configuration window and that window and come back to our test page. The last one we're going to open is our surge window and see the setup for our surge test. We can see from that surge test window that we're at 5600 volt surge voltage. That'll be our target voltage, VRAMP 25. The pulses are around 10. So that means at the end of the test at 5600 volts, it'll hit it again 10 times. The line-to-line EAR and pulse-to-pulse EAR are both checked. That means both of those test comparisons will be ran during this test. And they're both set at 2% threshold. Now that 2% may be a little tight for a motor, but the line-to-line can only be performed when the rotor is removed. And in this case, the rotor is removed. You'll learn more about these particular tests in other videos and in my class online course for motor testing. And I'll provide a link in the description of this video for that course. So we're ready to run the first test. We'll hit Run Auto. It says you've changed parameters. Yes, we want to do that. You have to hit two buttons to initiate the first test, which is a resistive imbalance test. The test says it's set for 3% imbalance. We entered our temperature estimation for the motor winding, which was 71 degrees Fahrenheit. It's right now performing a resistance test of lead 1 to lead 2. Gave a result, lead 2 to lead 3, and calculating that result. And also next would be lead 3 to lead 1. When this test is complete and we're below the 3% imbalance threshold, the tester would automatically move on to the next test, which is the MEG test. It says disconnect low voltage resistance leads and connect the high voltage leads. So it reminds us we've got to change the tester leads to the higher voltage leads and get rid of these Kelvin leads. And now we'll be connecting the high voltage leads to the motor phases. Be sure to have good ground wall insulation. Like on that table, you can see he's got a rubber pad. Also make sure there's separation between the phases and that you have a very good ground connection. Once we're back at the tester, it says hit the start. And the megohm test will begin at 2400 volts. The two graphs on the right, voltage is ramping up. You can see the voltage ramping up. The leakage current is the bar graph on the right. Right now it's at 7 microamps. Very low leakage current. It reached 2400 volts. The leakage current is 0.625 approximately microamps. And the megohms value is very high, close to 5.3 gigohm and increasing. This test will last for 60 seconds. It's a standard MEG test. If it drops below 100 megohm for any reason, it will trip. Also, this AWA tester has different scales. You saw when the red graph seemed to jump, that means the scale was changing. It has a scale at like 0 to 1, 1 to 10, 10 to 100 microamps, and up to 100 to 1,000 microamps. But anytime it crosses that 80% of that range, it will actually trip. So it doesn't always have to reach the 1,000 microamp level with the AWA tester. It just has to hit 80% of the scale range that it's in currently. It also has an arc detect in there that tries to detect if an arc has occurred and will trip immediately as well. All right, at this point, we have finished our MEG test successfully, and it's going to automatically go right into the polarization index. You can see the leakage current and the megohm result at 1 minute. The red pin trend is the leakage current. The black is the megohm. During the polarization index, dipoles align in the insulation. As they do align, the absorption current or polarization current will decrease, which is why that red line is decreasing. And as that leakage current decreases, megohms will increase. Our expectation is that good insulation will difference in 1 minute reading and the 10-minute reading will at least double. So that's the reasoning for the threshold to be at 2. So this test will continue for 10 minutes. Now we're going to go ahead and fast forward. Here it is at all the way to 5 minutes remaining. You can see the leakage current starting to flatten. And again, we fast forward to 3 minutes. The leakage current is still trending down, slightly flattening slightly, which means that the polarization current is almost completed. Dipoles are almost completely aligned. Our MEG result is 23 gigohm. That's pretty good after the 1 minute reading was 8.5. We've certainly doubled down to 5:55 seconds remaining in our polarization test. The DA in the right-hand corner there says 2.4. The DA is a dielectric absorption test, and that's posted there because at 3 minutes it was able to calculate the DA. The DA is the same thing as the PI, only it's the 30-second reading divided into the 3-minute reading. Small motors, we only run a DA. We don't run a complete PI because they'll polarize within 3 minutes. There's no need to waste 7 minutes of our life waiting on the polarization. So we've got 7 seconds remaining in this test. If it is successful, which it appears to be, we're going to move on. It'll automatically move on to the step test. And here we go. It's now performing the step voltage test. The blue pin is the voltage step that it made. And again, the red pin is the leakage current. The voltage will remain at the 3250 volt level for 60 seconds. There's approximately 30 seconds remaining in this first step. Leakage current is on the bottom right. It's right now at 0.24 microamps. And as soon as that 60 seconds end of step reading is captured, it'll be posted in this grid up on the left side of the chart. So after the first test is complete, we have our leakage current, and now it's ramping up to 4,100 volts. Our leakage current at the end of that step was 0.2037. Our megohm result was 15.9 gigohm. So we're now at 4,100 volts, leveled off, holding it for 60 seconds, and watching our leakage current. At any time the test set sees 1,000 microamps, it would trip. If it sees an arc detect, it would trip. Or if it's at 80% of its current measurement range, it'll trip. It will not trip if it's a nonlinear result in leakage current, which is also a pass-fail threshold for us. But we're the ones that have to watch for that and see that. And the way we can see that is now we got two measurements to look at, and we calculate in our heads the difference in the two leakage current readings at the end of step 2 and step 3. That would be about a 0.10 increment in leakage current. The next step increment should be the same, 0.10. We're now ramped up to 4,950 volts. When you see these leakage current increase like it does and then decay, that's simply the charging current and the additional polarization current that takes place when voltage is raised in that winding. The reason we're holding it for 60 seconds is for that, give that time to dissipate or decay, so that all we're seeing is actual leakage current through or around the insulation. We've just finished our third step, and actually our fourth step, and we can see the difference in leakage current between the third step and fourth step was, again, 0.10. We're very, very linear. This is a very good result with this test. We're now at 5,800, which will be our final target voltage and our final step. And I can see the leakage current is 0.5, which is what I would expect. So that was a successful test. That step test passed. And it will now automatically transfer into the surge test, which is our final test. The surge test is a test of turn-to-turn insulation. To better understand how the surge test interrogates turn-to-turn insulation, I invite you to click on the link in the description of this video for my online motor testing class. In the online class, you should learn why we test, how the test interrogates ground wall and turn-to-turn, and how to interpret data and results of each test. At this point, the tester is surge testing lead 1, discharging into the winding and producing a ringing waveform, and we don't want to see the waveform shift left or move frequency. At this point, it's testing lead 2 and raising voltage, and during each pulse, producing a ringing waveform at the same frequency as the previous pulse. Should there be a shift in frequency, ringing frequency, the tester can quantify that using the EAR graph. EAR graph stands for error area ratio. If it exceeds 2%, then it would trip the test. But any pulses on the EAR graph, which is that bottom box on the bottom right corner, are significant, and we would investigate those pulses. At this point, we're finishing with lead 2 and about to perform a surge test on lead 3. And again, surge test is interrogating the turn-to-turn insulation. It's the only test that can interrogate weakness in the turn insulation prior to it failing. I see no pulsing in the EAR graph. I see no shifting left of the waveforms. This was a successful test. And that completes the 5 tests that are performed: resistive imbalance, MEG, PI, step, and surge. Now we can go back now and look at our results summary to see this test. There's 2 tests that were performed. The one on the left is the one we just did. We can scroll down and we see our resistive imbalance. We can see our MEG result. Our PI result was a 3. Our step test levels at the top voltage. And our surge result. The pulse-to-pulse EAR was 0.1, 0.1, and 0.1. EAR between line was 1, 0, and 1. We're going to look at some graphs though, because we don't just take data. We look at interrogate the waveforms. We're going to look at the ringing waveforms first. This would be all 3 phases. They're right on top of one another. Very good symmetry in the motor. You can see the nested view of each phase. That's the different tests during the 0, I think it's 50% voltage and top voltage, the ringing waveforms of each phase or each lead. We'll look at the EAR graph next, and it's absolutely across the bottom. There's just no pulsing. That means there was no shifting of the waveforms on any of the 3 leads. Very good result. Polarization index graph is there, leakage current and megohm values. The PI result was a 3.0, DA was a 2.4. We're interested in that PI. It is above a 2, which is good. Anything below a 1.5 is undesirable with a PI result. And this is a step test. Those plots are the end of step leakage currents. Remember, they should be a straight line and very linear. Now we can click on that button. We'll see that green line. That's the line that we're looking for, to see that there's no erratic behavior in leakage and that line is very linear. If we click on the top help button and pick on tester information, we'll get a screen that pops up. And that screen are the some of the parameters that are set in the test set. And we can change those if we have the right password. The pulse-to-pulse EAR graph, EAR test compensation mode is where that blue highlighted box is. And that can be changed. We like to run a comp mode 3 with an AWA tester. Again, I'd like to thank Allen's Electric for allowing us to do these tests at their facility and their great employees that help us with these type tests and procedures that they allow us to witness. If you want more information on what these tests are, their function, uh, how to interpret the data, understand these tests completely, I invite you to go to the site motorreliability.teachable.com and enroll in the course on low voltage and high voltage motor testing. There's also a course on DC motors there as well. You can enroll in either one or both. I hope you find this video interesting and enjoyed it. If so, please hit like and possibly subscribe and support the channel. And thank you very much.